Well, gee, I think it might be a software related thing that's happening here. I don't know. Yeah, my internet connection sometimes is a little bit odd. It's stable. I don't know. I think it's a software thing that's going on. Because I'm tinkering. You have a lot of control over when you're using Arch Linux. Linux, and in particular Arch Linux, you have quite a bit of control over what you're working with, what you're working on. And yeah, I can kind of see a little bit of what's happening. And it's weird, to say the least. I don't really know why it's behaving the way that it has been, but anyway, so okay, here we are. It's definitely like a network related thing, I'm sure. I don't think it's like I don't think it's a physical thing, is what I'm saying. I don't know. Yeah, I don't know exactly what the problem is, but it seems to be, I don't know. It's Ghost in the Machine type of stuff going on here, where I think, because I could see when my computer is like picking up different IP addresses or whatnot, and it seems to just like run into issues at some point, and then it tries to pick up another IP address. It seems. I don't know. I don't know. Anyway, all right. Let me continue. So this is largest values from labels. And let's do that. Let's go ahead and do that. Okay. And this other one we can close now. See how quickly I can get through this one. See about this one. And then I think after that is, I think I'll take a break after that. I think I'll stop after that. Maybe stop for the day. There is a set of n items. You were given 2 integer arrays, values, and labels, where the value and the label of the ith element are values of I and labels of I, respectively. You are also given 2 integers, num wanted and use limit. Choose a subset S of the n elements such that the size of the subset S is less than or equal to num wanted. There are at most use limit items with the same label in S. The score of a subset is the sum of the values in the subset. Return the maximum score of a subset S. So values 54321, labels 11223, num wanted 3, use limit 1. Output 9, the subset chosen is the first, third, and fifth items. Excuse me, first, 1, 2, 3, third, and 1, 2, 3, fifth items. 5, 3, and 1. Okay, I don't really understand the question. There's n values and n labels. There's 20,000, and the values are between 1 and 20,000. So I could, if I want to do a counting sort, I can use a counting sort here. 1 to n, num wanted, and use limit. Okay, what are they saying? Given 2 integer arrays, values, and labels, where the value and the label of the ith element are values of I and labels of I, respectively. So it has a value and a label of an item. Okay, you're also given 2 integers, number of wanted and use limit. Okay, not sure I understand. Choose a subset S of the n elements such that the size of the subset is less than or equal to the number wanted. Okay, so we're going to pick as many items as there are wanted. So 3 items here, 3 items here, and 3 items here, right? It could be at less than or equal to, so it doesn't have to be exactly 3. It could be 3 or less. Okay. Excuse me. There are at most use limit items with the same label in S. Oh, I see. So there's at most 1 item with a particular label. So it's going to be 1 from 1, 1 from 2, and 1 from 3 at most. Same thing over here. So there could be at most, well, there's only, most 1 from, the most 2 with the same label. Okay, I think I understand. So we could pick 2 3s, so 4 and 3, first, second, and third, and then we could pick a 1. Yeah, first, second, third. Okay, cool. And then finally, the score of a subset is the sum of the values in the subset. Turn the maximum score of a subset S. Okay. Is label sorted? No. Well, okay. Turn the maximum score of a subset S. Everything's 20,000. Yeah. Everything is what's the word? Everything is bounded by 20,000. So it gives me actually a lot of room to breathe as far as like using frequency maps and counting sort and things like that. Okay, so all right. Subset chosen is the first, second, and third items. Okay, so we want to maximize the value, maximum score, but we don't want to use more than unwanted, and we want to use at most the use limit. Excuse me, use limit of 1 can't actually use all 3. So we would normally, since these numbers are positive, we would want to use as many as we can. Up to unwanted. All right, so interesting. I think we probably want to sort by value and by labels. I think you can do this with a heap. We just want to keep track of the frequency of the labels. So grab the next largest value, and it has a label. Next largest value, if it had, and if we don't reach the use limit for that label, if we've reached the use limit for that label, then we toss it. I think that's how I want to do it. So we just have to keep track of the frequency, the use frequency of a particular label. And we can just sort the indices by their values. I think that's the way to go. Okay, so let's say values, labels, let's rename these. So max num or total or wanted, and then limit. Keep it simple. So we'll say frequency is going to be the use frequency. Let's say the bound is 2 e to the 4th, right? 20,000 plus 1. I think something like this is fine. So there's a use frequency is what I want to keep track of. I want to iota. So constant n is vs.size. Int indices of size n. Let's go ahead and iota those indices starting from 0. Let's sort. Let's use a comparator. Which is going to be index 1, index 2. And just return. It's going to be V's of A less than V's of B. Oh, we want to sort the other direction, actually. So I got to sort by value of the indices. So standard sort indices plus n using the comparator. And now they're going to be sorted in decreasing order, and we're going to have a for loop, a few for loops. Int, we'll say target 0. Target is less than wanted. There's another index or current or I 0. I is less than n. Target is less than wanted. Yeah. Increment I at each point. constant val or item index is going to be indices of I. And now we can say result Okay, so the idea is we're going to loop, look at a value, and it's going to be from the larger values downwards. And we're going to increment the, so if the use frequency, so the value is that VS of item index, and the label is LS of item index. Okay, so if the use frequency of the label is less than limit, then we can take this value, so use frequency of label increases by 1, and the result increases by the value. Otherwise, we skip and the target increases as well, right? Use this, increase the target, and increase the use frequency. Otherwise, we skip this element altogether. We don't add it to the result, we don't increment the target, we don't increment the use frequency. I think that's it. That's the whole thing, that's the whole algorithm. It's like very straightforward. You just skip some of these elements if we've already used too many of them. Yeah, it could just be frequency, but use frequency is maybe a little bit more cogent. Yep, done. Okay. Let's try like another test case with 1, 10, 2, 4, 3, 4, 5. 1, 2, 3, 4, 5. Let's just make them all zeros. And let's do nums wanted is 4 and use limit is 3. Something like this. I think this is it. I try to make something a little more complicated. 10, 9, 3, 2. Could add 1, 1, 3, 2, 3, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, did I do that right? Yeah, I think so. And let's do nums wanted is 3 and use limit is 3. Okay, I don't know. I think I got it. I'm not gonna, I probably shouldn't spend too much time trying to think of different test cases. Unknown network error. Okay, hold on a moment. This may or may not work. Let's try one more time. Try one more time. This could be wrong. I don't know. We'll see. Yep, got it. Okay. I was gonna say I think it's right. I don't want to spend too much time. Yeah. All right. Let's submit it a few more times. Go for 5 submissions. Yeah, that's fine. I mean, I don't really want to explain this too much. I think it makes sense to those interested. It should be linear time. No, I'm sorry. N log n time. Linear rhythmic time. 1, 2, 3. 2 more. Linear rhythmic and kind of hard to explain exactly. 92% is pretty good. Exactly what's going on here. The sorting, by the way, could be done using a counting sort. I didn't think about that, but it's maybe easier to think about it. Yeah, 98% is pretty good. Yeah, so I think this can get 100% of use counting sort here for the iota part, but it's also, it's not that easy to use counting sort in this instance because you want to keep track of the indices themselves. So you probably would want to use like an array of indices that have a certain value, which is a little more complicated, but could still technically be done that way. You could still use counting sort. I don't think it's better to use counting sort here. Maybe I'm wrong. I could be wrong, but it's still reasonably fast, even with this sorting algorithm without using counting sort. You could use counting sort for this too. It's a very straightforward approach, I would say. This is obviously linear pass afterwards. So pretty good, not bad. Almost 100%, very close. I think if I modified it a little bit, I probably could get 100%. Let's see. All right, stop there. I think that'll be my last question for the day. I think that'll be it. So yeah, thank you for watching. If you like this video, give it a like. If you like this sort of content, give me a follow, subscribe, and yeah, thank you. Talk to you soon. I think that's it for today too. So.